This lecture is actually one of 4 shorter lectures that will fit into classes 11 and 12, but the material all fits together in one package, so the slides that will be used for this will be given to you in one package of slides. It'll be rather long, maybe 40 or 50 slides altogether, but the actual lectures will be split into 4 parts. This first one is to review quantum statistics and thermal distributions of the probability that you find a particle in a given state, and folding into that the idea of the density of states. Once we have the general idea of the density of states, then we can apply it to special cases, and we'll talk about a gas, the concept of a gas that is made up of photons inside of a box. And we'll talk about the concept of putting fermions into a quantum mechanical box. And then the ramifications or the ideas that come from that, where we actually consider fermions confined in a space the size of a star. So we'll go all the way from nanoscale quantum mechanics to macro scale, astronomical scale quantum mechanics in this portion, these 2 lectures in the course, 2 classes in the course. Again, this will be split up into 4 lecture segments. So first, review of quantum physics. Quantum statistics, rather. So the distributions that we deduced at in the last class were the important quantum mechanical ones are the Fermi-Dirac distribution, and the Bose-Einstein distribution. Fermi-Dirac distribution is the occupation of the, let's say, not just probability of occupation, it is the number of fermions that can occupy a particular state in the system. And the maximum number of fermions that we can put into a particular set of quantum numbers, excluding spin, would be 2. If we include spin, then we can only put 1 electron into each allowed state in the system. So the Fermi-Dirac distribution has a maximum value of 1 when we work it out. All right? This would be the energy of the state that we're looking at, what the occupation of that state would be. And the mu here is a term that expresses what's called the chemical potential of the system. And for Fermi-Dirac distributions, that mu is frequently called the Fermi level or the Fermi energy of the system. So you'll see it written as E sub F, Fermi energy. This is the Boltzmann constant and a temperature in Kelvin. So the Fermi-Dirac distribution looks for energies greater than the chemical potential of the system. Looks like this. It drops off when we get far enough away. It simply drops off exponentially. The Bose-Einstein distribution applies to bosons, integer spin particles, and a given state in a Bose distribution, Bose-Einstein distribution, can hold many bosons. There's no limit on the number of bosons that can be in a particular state, and the number that we find in a given state is going to be equal to this distribution function here, which when you look at it, when the chemical potential is equal to the energy, or the energy is equal to the chemical potential, then this term is 1 and that term is 1, and the number of bosons that can sit in a state at the chemical potential is actually equal to infinity. It turns out that we can never have a boson in a state exactly equal to the chemical potential because of the finite size of a system. But That's what the mathematics tells us here. The Maxwell-Boltzmann distribution is an approximation to these two distributions for energies that are large compared to the chemical potential measured in terms of the product of the Boltzmann constant times the temperature. At room temperature, that product is about 1/40th of an electron volt. So if the energy here is much more than 1/40th of an electron volt, then these two distributions actually reduce to the Maxwell-Boltzmann as an approximation. The Fermi-Dirac distribution has an unusual behavior, and you've become, I hope, accustomed to that idea in looking at the occupation of states in an atom, for example, as we start at the bottom of the energy distribution and then start filling up states. We fill them until we run out of electrons, at which point the occupation of the states goes from 1 to 0. Remember, we're counting a particular spin state as being a state. So there are two spins that go into an energy state, but the probability of occupying a particular set of quantum numbers with the spin specified is 1 when the energy of the particle in the system is much less than the Fermi energy or the chemical potential of the system. So the probability that an existing state is occupied is given by this Fermi-Dirac distribution here, right? At the chemical potential, that probability is 1/2, and that is what is shown here in this sketch here. As we raise the temperature, this distribution of occupations becomes broader and broader. At 0 temperature, we go up to the Fermi level. The occupation drops from 1 to 0 in an infinitesimal space, so Heaviside function, and then at 0 above. At finite temperature, it slowly decreases from 1 through 1/2 to 0. It decays exponentially on this side, and it leaves 1 exponentially on that side, or approaches 1 exponentially on this side as we lower the energy. All of this, by the way, has to be subject to the constraint that the number of electrons or fermions in the system is fixed. This is not true of bosons, of photons in particular. Right? The number of photons in the system doesn't have to be fixed. But for the Fermi-Dirac distribution, where we have particles that have mass and specific quantum numbers, then the total number of particles in the system has to be fixed. So all of these distributions have to be subject to this. Now you notice that there's this extra term in here that I haven't talked about yet. That is called the density of states, and now I'll talk a little bit about that. So to calculate the physical properties of a system, we actually need to know just how all of the states in the system are occupied, right? Properties like electrical conductivity and heat capacity depend upon not just the computation of occupation probability of a state at a particular energy, but how many states are there in that range of a particular energy? How many states are there near the Fermi energy? How many states are there far below the Fermi energy? That will turn out to be quite important in calculating the properties of a system. So we're going to start out here now by attempting to count states and to come up with some distribution. And as a sort of sketch that I'll make off to the left-hand side here, I'll draw the example of the atom that we had before, that we had some energy levels in an atom, and maybe those energy levels are very close together in one range, and then you jump up to a new set of quantum numbers, and then you have a bunch of energy levels that are differently spaced here, and then maybe I've got some other energy levels in here, all right? But then there's a big space, and then we jump up like so, all right? This would be a distribution in energy of the possible occupations, of the possible states that we have, right? And then we go in, we put electrons into those states, and we start filling them up. And we count each spin state as a state, so we've got one electron in each allowed state here. And then we fill up until we run out of electrons, and then we would call that the chemical potential or the Fermi level of the system, just as we run out of electrons. It's not so hard to do this for an atom where we're just starting and we count up and we know the energies and we start filling things up. When we're talking about a solid, then what might be important here to think about is the fact that, for example, as we come up towards the top here, towards the vacuum, these states are going to get closer and closer and closer to one another, so that they essentially are indistinguishable from each other, all the possible states up there. And it's much easier to express this as a number of states per unit energy width. So we take this system and we break it up into, maybe make energy bands here. You know, I'm just going to say anything that's between here and here, I'll call a band. All right. And then anything between here and equal distance up and here, I'll call a band. And everything between here and here. And then we analyze the system in terms of these brackets of energies. How many, maybe the Fermi level sits here, and then we say, how many states sit far above the Fermi level? How many states sit far below the Fermi level? And what we'll be interested in is the actual, what we call the density of states, how many states per unit energy we've got in various ranges here. So I'm going to take as my example one that we're going to use again and again throughout this segment of the course. The energy levels of a particle, in this case, in a cubical box. All right, so quantum well. Let's make it infinitely deep to make the wave functions easier, right? Then we know that the space wave functions look like an amplitude times sine kxx if I set this point here equal to 0 and this side here equal to L and 0 L. Which one am I missing? This one here. 0 L. So there's my cube with coordinates x, y, z, and the wave functions that are permitted in this box correspond to, within the box, they've got to be sine functions. Then I've got to satisfy the boundary conditions, and when I do that, I find that the allowed wavelengths for particle in a box are twice the size of the box in a particular dimension divided by an integer. Those are the discrete wavelengths that are permitted in the box. Then the wave vectors that would be associated with those wavelengths are 2 pi over the wavelengths. The momenta that are allowed are Planck's constant divided by the wavelength. So the momentum is discrete as well as the allowed wave vectors, as well as the allowed wavelengths. And you know that the energies are discrete as well, all right? So a wave vector along one axis, let's call this the x-axis over here, all right? Along the x-axis are going to be allowed to be plus or minus pi integer divided by the length of the box in the x direction, y and z. Remember that the total energy for a particle that has mass is p squared over 2m momentum squared over twice the mass, which we can rewrite as h bar squared wave vector squared over twice the mass. But we know what the wave vectors are. So the allowed energies in the system will be this, Planck's constant squared divided by 8 times the mass of the particles in the system, the length of the side of the cube squared times nx squared plus ny squared plus nz squared, where nx and y and nz have to be integers. Okay, so we know that already. We learned that in Quantum Physics 1 or earlier, that those are the allowed states of a particle in a cubical box. So what we just observed was that there are discrete momentum states, or discrete wave vectors. There are, as I chose on the previous slide, I chose a boundary condition in which the amplitude of the particles goes to 0 at the boundaries. And in that case, we get the allowed wave vector is equal to pi times n sub x over L. Another boundary condition that is applied to systems like this is, and probably a little bit more ubiquitously than the boundary condition that goes to 0 at the boundary, all right, are what are called periodic boundary conditions. That is, that the wave vector on one side of the box has to be the same, not the wave vector, that the wave function on one side of the box has to be the same as the wave function on the other side of the box. So in that case, I put a full wave in there, and the wave function here is exactly the same as there. That would be true even for this case up here, where the ground state, the lowest energy state, would look like that, right? But in this case, I'm demanding that the wave function's periodic no matter what it is on the boundary. And so I could have a situation where it looks like this. So this would not be a well, right? If I start with a maximum here, then I've got to return to the maximum on the other side. And what that demands, that particular choice of boundary condition demands, is that the wave vector in that direction has to be 2 pi times an integer over L. All right. Most textbooks in this section of the course, once we've gotten away from an actual well, use periodic boundary conditions. That's because that's sort of the standard way of analyzing things in solid state physics. For particle physics, they would probably use the upper one, right? That the wave function must be 0 on the boundaries. But because the textbooks tend to use this more frequently, I'm going to use this in the rest of the, I'm going to use this in the rest of the lectures. So I'm going to introduce a way of thinking about these states and how to count the states up. And I've already sort of summarized all of this already with the ideas from the particle in a box, right? I have the constraint now based upon periodic boundary conditions, right? That the allowed wavelengths are equal to the size of the box divided by an integer, right? Not twice the size of the box. And so this is written this way, that the allowed wave vectors are 2 pi times an integer divided by the length of the side of the box. And because I'm going to make a cubical box, I'm just going to use L here. And the overall wave vector then is kxi plus kyj plus kzk, right? And the magnitude of k is kx squared plus ky squared plus kz squared to the 1/2, right? Why is this useful? In part because we have simple relationships between the energy and the magnitude of the wave vector. Energy for photons is h bar times the wave vector k. And for particles with mass, the energy, classical particles being treated classically, non-relativistically, the kinetic energy is equal to h bar squared k squared over 2m. So Once we've got an idea of what K is, what the allowed Ks are in the system, then we can calculate allowed energies. So we're going to think about this particle in a periodic system, a particle in a system where the wave function has periodic boundary conditions in terms of the allowed values of K. So I've just got Kx and Ky here. This would, in 3 dimensions, go in the other direction as well, Kz, but it can't be represented. When we look at the relationship that we had for K, which was that it was Kxi plus Kyj plus Kzk, right? And that the allowed wave vectors were 2 pi times an integer divided by L, then we can make a representation of the allowed states on a wave vector scale here. So Kx along this axis, Ky along this axis. The allowed Kx's are 2 pi n, an integer, I'll label it x, divided by L, all right? And so this is what I've sort of got up here, all right, for Kx is here, all right? So each one of these states corresponds to a different integer, and along the y-axis, each state corresponds to a different n sub y. And because the allowed K states are simply separated by integers, that means in this set of axes, the states are equally spaced. They're uniformly distributed throughout space. And in this K space, momentum space, the volume that's occupied by one state is 2 pi over Lx, that's that distance, times 2 pi over Ly, that distance. In 3 dimensions, the K space volume occupied by each momentum state is, so I'm going to write K space volume here, 2 pi over Lx, the size in the x direction, 2 pi over Ly, size in the y direction, 2 pi over Lz, the size in the z direction. So this does not have dimensions of volume. In fact, it's got dimensions of 1 over volume. But if I label it as sub k, it means on these axes, the space that's occupied by one of these states is that product. Okay? For a cube, it's pretty simple. All right? The volume in K space, the space that's occupied in K space for one of the states, one of the wave vector states, is 2 pi over the length of the side of the cube cubed, or 2 pi cubed over the actual volume in real space of this sample of this material that we're going to model. So to summarize and put it in a sort of a tighter format, right? For waves that have to obey periodic boundary conditions, the density of states in K space is the volume occupied by one space, is 1 over the volume by one state occupied in K space, right? I've put an n here because I'm going to indicate the dimensionality of the problem. That is, if I have a one-dimensional system, then n is 1. A two-dimensional system, and by the way, these dimensions are meaningful in an experimental sense in that we actually do find systems that behave like one-dimensional quantum mechanical systems and two-dimensional quantum mechanical systems. So this dimensionality has meaning. So the density of states in K space, right, is 1 over the space occupied by one state in K space, right, or the real volume in K space the real volume in real space occupied by the sample, all right, by the thing that we're calculating on, divided by 2 pi to the nth power, where n is the dimensionality of the space. We're going to frequently want to calculate the density of states as a function of the magnitude of k, not just how far apart the states are, how much volume does a state occupy, but because energy, for example, only depends upon the magnitude of the wave vector, then we want to know how many states occupy a volume between k and dk in various dimensional systems. And so using this cube approach that we took here, the volume of a cube, we find that the density of states in k space, right, as a function of the magnitude of k. I'll have a sketch in a minute, I hope, that will clarify this. So we're only interested in not in the actual spacing between the states, but in how many states there are in a certain magnitude of k range, right? So that's the real volume in 3 dimensions divided by 2 pi cubed, right? Times, now, in k space, the volume that is occupied in the range at value k in range dk is the volume of a shell of size k, of diameter, of radius k. So 4 pi k squared dk is the volume of a shell. And the number of states per unit k space volume times the volume of that shell tells us how many states there are in that shell. Density of states then in 3 dimensions. If I have a 2-dimensional sample, so I've only got kx and ky, then the density of states in k space in 2 dimensions is the area of the sample divided by 2 pi squared, all right, so 4 pi squared, times the area of a shell of a circle of radius k and thickness, width dk. So this one I could draw. I'm calculating how many states sit at a radius dk between k and k plus dk. How many states are there in here? And in 1 dimension, we can do the same thing. How many states in a 1-dimensional sample? And my volume in 1-dimensional case is just the distance between 2 states. Once we know the density of states per unit k, then we can convert that to density of states per unit energy if we know the relationship between energy and wave vector. The density of states in energy is actually always going to be equal to the density of states in k space. So I've got I should actually write d of k here, right? Which we just calculated for that cube situation, which applies in general to almost any volume, because in the end I derived it using a cube, but in the end I converted the length of a side directly over to L cubed is the volume. So what we're talking about here is a relationship that applies to any dimensionality and any actual shape as well. So the density of states as a function of the magnitude of K, which is related to the energy, the density of states in energy, is that density of states in K space, where now what we do is substitute E for K in that relationship, divided by dE dK, the derivative of the energy with respect to K. For photons, for example, K is equal to E over h bar, and dE dK is equal to h bar, because E is equal to h bar K. dE dK is just h bar. So then, writing that out, our density of states in K space was the real volume of the sample divided by, well, I'm going to leave it at this. All right, 2 pi squared K squared. All right, yes, I'm okay with this. I'm sorry, I just hesitated. I had to divide out some 4 pi. I had to multiply 8 pi cubed by 4 pi. That's where that came from. So the actual volume of the sample divided by 2 pi squared times K squared. All right, that's the density of states in K space. All right, and now what I'm going to do is rewrite K squared in terms of energy. So I'm going to make a substitution in there. This gets substituted in there. All right. So now I turned it into a function of energy, and I have to divide by dE dK, which is just h bar. So the density of states as a function of energy for a particle in a box is the real volume of the sample times the energy squared divided by the constants that come out of this conversion, 2 pi squared h bar cubed. So now we know the density of states as a function of energy.